So today inshallah we are going to continue working with atoms, and basically we are going to do a new activity, a new important activity, which is importing CAD assembly into atoms and use it to build or create a new model. The model that we are going to import is this model, Geneva mechanism. In this mechanism, we are going to show some kind of intermittent motion. The activities that we are going to do through this workshop, we can say we are going to import the CAD assembly, SolidWorks assembly, and we are going to talk about different assemblies that you can import. We are going to also work on change the grid settings in order to match the models that we are importing. We are going to work on bodies, the geometries that we are going to have from SolidWorks. We are going to utilize them as dynamic parts into atoms, and we will see what are the main steps that we have to go through in order to have them working as dynamic bodies. And after having the parts as bodies, we are going to create joints. We will connect them using the proper joints, the proper types of joints, and we are going to add motion, so this motion can rotate the system or drive the system. In order for the Geneva mechanism to work, it must have some kind of contact force modules. So we learn how to add different contact modules. We learned this before, but we are going to repeat this again for this mechanism to function. We are going to add motion driver, and we are going to again use the step function for the motion driver in order to smooth the motion. And then we are going to add a new feature. We are going to replace this motion driver or kinematic driver with an electric motor, so you can have more realistic driving system for your model. And we are going to create an animation for the system. If you look at the main components in our mechanism, basically in the mechanism we have a base, and this base will carry all the parts. I have the Geneva wheel. This Geneva wheel is carried by a shaft. So most likely this Geneva wheel would be fixed to the shaft, and the shaft will be rotating with respect to the base. And then we have this disc that carries an arm, and the arm has this contact pin. The contact pin will drive the Geneva wheel when it attaches the wheel, when it connects with the wheel at this point, it will slide inside this slot, causing the wheel to drive. I would like to show you an animation for this mechanism so that you can understand how the motion is going to look like. So here we have the input is driving this disc. We have the contact pin is going to connect inside this slot and slide inside the slot. Due to the contact between the pin and the slot, it will cause the wheel to rotate. Now, as you can see, the pin is connected to this arm, so we can assume those are kind of fixed to each other. The pin is fixed to the arm, and the arm is also fixed to this disc. This disc is also fixed to this shaft. The shaft is driven by the driver that drives this joint. The shaft is connected to the base using a revolute joint. On the left hand side here we have the Geneva wheel with its shaft connected to each other, and then the shaft will be connected to the ground with a revolute joint. As you can see, this disc is preventing the wheel from rotating without contact between the pin and the slot. So when we model this system, actually what we will need to have is one contact force between this geometry and this geometry, and we will see why. And we will have to have another contact force between this pin and the Geneva wheel. As we said, we are going to have, at the beginning, we are going to have a driver, and then we are going to replace the driver later on with a motor. So we'll learn how to do the motor later on. Okay. So when we start with the model, we are going to download the assembly. This assembly I got it from CAD. I just downloaded the assembly to my desktop, and I'm going to use it for the demonstration. So this assembly here, this zip file contains the parts and the assembly file for SolidWorks. I saved the assembly into this directory, and I'm going to have all the files inside this directory. In order to see the files, I'm going to extract this zip file. So I'm going to extract files, extract here. This is going to generate 7 files. The one in the top here is the assembly file, SolidWorks assembly, and then we have Geneva 1, holder, locking disc, part 1, part 4, and pin. Those are the parts that we have in this model. Now I would like to import this assembly into Adams. So I'm going to go to Open Adams, and I'm going to start a new model. In this new model, I'm going to call it Geneva mechanism. And I'm going to save the model where I have the files. So here is our folder. Import CAD. So I'm going to save my model inside this folder. So I'm going to select the folder. So this is my Geneva mechanism. And remember, we are using the units millimeter, kilogram, Newton second, and degrees. I will click OK. Now I don't have any bodies, no joints, I have only the gravity. If I click on save, it's going to create the pin file, the binary file for me, as you can see here. But as you can see, still empty, it doesn't have anything. So we're going to import the SolidWorks assembly. In order to import, we'll go to File and select this Import from the File menu. We have, at this moment, we have this menu here. This is where we import. What do we want to import? What we want to import, we have to go and select from this drop-down menu. So as you can see, the default is importing Adams view command file. Adams view command file is what we imported before, but now I'd like to import an assembly. If you click on this drop-down menu, you will see different options that you can import. As you can see, you have Adams view command file, Adams view Python if you have a script that you want to import, and other things related to Adams. And over here you can start seeing Parasolid, which is basically graphics, and here you have CATIA models, and then you have IGES. IGES is one of the very popular format to save graphics and exchange graphics between CAD system and also between analysis systems. So sometimes you will find you can import your model, save your model or assembly from SolidWorks as IGES and import it here in our Adams. Also you can import from Autodesk Inventor, Pro E, other formats that you can import. What we are interested in right now is the SolidWorks assembly. So here you can see SolidWorks, either SolidWorks part or assembly. So I'm going to select this. This is going to activate the the translator that's going to translate the assembly from SolidWorks into Adam's model. Now, as you can see here, once we select what we would like to import, the interface is changed. Now it's asking which file do you want to read. So in this box right here, I will right click and select browse, and I'm going to browse to where I saved my model, where I extracted the files. So I extracted it here, and as you can see, we have SolidWorks assembly and SolidWorks part. For this model that we are going to import the assembly, I will select the assembly file here, Geneva_wheel dot SolidWorks assembly. Now I'm going to click open. So you see the file, the directory, and this is our assembly name. Now it says part name. I don't want to import part. Actually, what I would like to import is the whole model. So I'm going to change this. Instead of part name, I'm going to select model name. And we already have the model. So what I'm going to do, I'm going to import this assembly and save it into this model. In order to do that, I'm going to right click here and select the model. You can now select the guesses, which is going to give you the name of our currently open model. And what is going to happen is going to import the parts, the geometries of the parts from the assembly file into our model. Now this scale is very important. If you are, depending on how did you create your model, if you created it using meters and you have the units in Adams right now is millimeter, then you can use the scale here to convert the units. If you can make this scale 1000. If you created the model using inches and you would like to analyze it based on millimeters, then you can do also the conversion right here. Location and orientation. Usually you can control where are you going to place this model for parts, but because we are importing a whole model, we can just, Adams is going to import it with respect to the default with respect to the default origin of the system. Those are some kind of options for the geometries. We are just going to keep the default for those. So what I have, I selected the SolidWorks assembly, and then we defined our files that we are going to import, and we defined the models that we are going to add those parts into, and we define this as a whole new model. Now I'm going to click OK. So Adams is going to read the geometries and import them into Adams environment. This may take a little bit while depending on how many parts you have in your model, also depending on how much geometry, how complex your geometry is. Also depends on what type of geometries you are importing. So just give it a few seconds and it will pop up again. Okay, so now as you can see, Adams have completed the importing of our models, and as you can see, the geometry appears in the middle here, and also it appears list of the parts appear in the tree, and it gives me this warning message. So you don't have to worry about this for now. I'm going to clear it and close it. But now you can see the parts have been created. Under every one of those parts, you can see you have a solid geometry, and you have marker for the solid, the base, the marker solid, and there is nothing else. What we are familiar with is that every part should have a center of mass. Now I don't see center of masses for the parts. And as you can see, the model is here. But as you can see also, this model has orientation different from what we are using. This model was created at certain coordinate system different from the XY system that we are using. If you would like to see the model, you can click on this isometric view. So this is the model in wireframe. We can fit it. If you would like to see it in shaded, you can click on this icon. So now you can see the parts of our model. So now this is our model, the model that we have imported. As you can see, we have list of the bodies here. And if I look at the isometric view and fit the model, I can see the model has parts. Those parts I can look at the shaded and wireframe. You can see the different components here. Now, if you think this model can work, I don't know. So maybe we can check, run a simulation to see if it's going to work or not. If our system can work, what we should see is that the model should fall under the effect of gravity. So if I run the simulation, if I run the simulation for 1 second, you see we got this simulation operation failed. And if you look at the errors, you can get some understanding about those errors. So what does it mean? So if we look at the error here, it says the Prost initial solution detected a singular Jacobian matrix. So there is something in the mathematics itself. Here it says a constraint equation that became almost redundant. So this is something related to the joints, but we don't have joints. The second here, the second cause, it says a massless part is in the model. So this means we might have a part that doesn't have mass. So this can make sense. So let's go and check our model. Does it have masses or not? If I start by clicking in any one of those elements, for example, this is our Geneva wheel. If I right click on the Geneva wheel and select the Geneva wheel, select modify. If I select modify, as you can see, it says the mass properties are based on user input. And because they are based on user input, there is no values for the mass or the inertia. And eventually this is true. We don't have masses for our parts, and this is why the operation failed. So what we need to do now is to define inertia properties for each part. The most appropriate way to define the inertia is basically to define the mass and the inertia properties based on the geometry that we have imported and based on the material of each part. So instead of using user input inertia, I'm going to select geometry and material type. So I'm going to change this to geometry and material type. The geometry is already imported. So Adams is going to use the geometry to compute the volume, and I need to define the material type. By default, I'm going to choose steel for all the parts. If you have different materials in your model, you can change the material to the material that matches your physical model. So in order to define the material type, I will right click on this text box, and then I will go to guesses and select steel. Now notice two things are going to happen. If I click apply, Adams is going to take the mass, the geometry, compute the volume, multiplied by the density, and use this density to compute the mass and moment of inertia. Also, Adams is going to use the geometry to identify where is the center of mass is going to be located and it will create a marker for the center of mass of our geometry. So if we look at this part here, you can notice what is going to happen. If I click apply, what happened? Adams created the center of mass marker here. It's already in the middle because the Geneva wheel is symmetric. So this center of mass is going to be, center of mass will be coincident with the geometric center of our geometry. Now, how about if I would like to see how much inertia or how much mass do I have? I can click on show calculated inertia, and it will give me the mass in kilogram, and it will give me the moment of inertia around the different axes, and this moment of inertia will be kilogram millimeter squared. So now we have done this for our Geneva wheel, so I'm going to click OK. I will have to repeat the same thing for all the other parts, so I don't get a problem with the inertia. So I will click on the holder, right click, select modify, material, geometry and material type. Again, define the material using steel. Again, we have the center of mass have been created for this part right here. Locking disk, so I'm going to modify, define mass by geometry and material type. Material type, right click, material, gases and steel, click OK. You have the center of mass is created. Notice the center of mass will not be coincident with the geometric center, because it will be shifted a little bit from the geometric center. Repeat for the remaining parts. Now I got all the parts right now. As you can see, all the parts, every one of them has center of mass, which means I already did all the definitions correctly. To make sure that those definitions are correct, I'm going to run the model again, and as I expect, all the bodies shall drop down with the same speed, because they have the same acceleration, gravitational acceleration. If I click simulate, as you can see, all the bodies have moved together. At this point, I'm going to save my model, no backup, and now I have the model which I can start working. So now we would like to change the color of the different components so that they can be differentiated from each other. In order to change the color of the component, what we usually do, we select the geometry of the component, not the part. We select the geometry itself, and then right click. And now we are going to change the appearance. So we're going to click on this. By default, Adams have chosen this color. I would like to change this color, so I'm going to delete this color, and I'm going to right click, and you will find the colors here. So let's see what Adams has for us. It's suggesting this list of colors. So right now I'm going to select blue and click apply. So now, as you can see, I can select the colors that I'm interested in, and I can do this for every one of the solids that we have here. So here I'm going to click OK. I changed this. I'm going to change the shaft, this shaft right here. Okay, so if you go to this, what is the shaft? I have shaft here. So let's give those parts names. instead of just having locking body and so on, let's give every one of those a name. So I will start from the bottom here. I'm going to call this Geneva wheel. So I'm going to click and click again. You see the name. I will going to change the name, Geneva underscore wheel. So this is our part right now. It has the new name. And this one is the holder body. I think one holder is enough. So we're going to change this to holder. And then you have locking body, locking body. One locking is enough. Locking disk. And then you have part 1. This is actually the base, this base right here. So I'm going to call this base. Part 4, this is actually the Geneva wheel pin. So I'm going to call this Geneva wheel shaft, like this. And then you have pin body. I'm going to call this contact pin. And then we have the last body, which is the locking disk shaft. So I'm going to change the name LED locking disk underscore shaft. So now I have every one of those bodies has distinctive name. I'm going to change the colors. So the shaft, let me give this shaft and this shaft a color yellow. So I'm going to select the color for the shaft. This is the geometry. Right click and select appearance. This color, I'm going to change it to yellow. And the same for this shaft. So I'll go to Geneva wheel shaft. Right click, appearance. Actually, you can type the name of the color itself. So you have yellow, type the name like this, and click OK. So now I have the two shafts has yellow color. Now I need to color also this locking disk. So I'm going to make this locking disk green. So I will just type green. And then I have the holder. So this is the holder. I'm going to change the appearance. I'm going to make it red, like this. And then you have the last body that doesn't have color is actually this locking pin or the contact pin. So I'm going to change the appearance, and we can make this in a different color. Let's make it light blue. So we can say sky blue. Apply. If you don't like the color, you can change it. If you would like to change the color of the base, it's up to you. I think this color is very bright, so we can choose more dimmed color. So maybe you can select gray, if we have gray. This is black, green, blue gray, dark gray. So let's try dark blue gray. That's very light. So let's take another color here. Coral. Very bright. I'm just going to put it white. This is like that. So now, as you can see, I have distinctive color for each one of those bodies. Now, if we remember the functionality, now we change the appearance. If you look at the tasks that we need to do, we have done most of the tasks needed so far. So here I have changed the materials, calculated the inertia, improved the graphics. Now we would like to work on the joints. If you look at the joints, if we look at the animation, you can see the base should be fixed on the ground. Those three bodies, those four bodies, the contact pin, the holder, locking disc, and the shaft, all of those are moving as one piece, which means those four bodies are locked together. Also, you can see the Geneva wheel and the Geneva wheel shaft, they move together. Look at the rotation, you can recognize that they are moving together. And the shaft of this disc and the shaft of the Geneva wheel are rotating with respect to the base. So this gives us an idea about what type of joints we would like to have. What we need to have is this base will be locked to the ground, it should not move. Those four bodies should be locked together, and this Geneva wheel and the shaft should be also locked together. So how do we lock those bodies? We lock the bodies together by using this type of connectors. So we'll go under connectors. You will see one of them is called fixed joint. The fixed joint is actually the locked joint. So if you click on the locked joint, here you can see how do you create it. You create it by locking two bodies. So we're going to select two bodies, one location, and we're going to pick the two bodies. So now if you move your cursor, you see in the status bar at the bottom of the screen, Adams is telling you you are creating a fixed joint from two bodies at one location. Select the first body. We're going to lock the base to the ground. So now Adams is showing the ground. Now I will click. Now Adams in the bottom status bar is asking, select the second body. The second body, I will move my cursor until I reach the base. You see the name of the base. Once you see the name of the base, you can click. Adams is asking for selecting a location. At this moment, the location of the joint doesn't matter. So I'm going to select just this corner. Once you selected the corner, as you can see, Adams created the locked joint. This big lock represents the fixed joint. And because this locked joint is between the ground with another body, you see those hash lines. Anything connected to the ground, anything grounded will have this hashed indicator. So now I have the base is fixed, the other body is still free. So now what I expect, if I simulate the model, the base will be fixed, not moving. The other parts will fall down again. So let's check that. I'm going to simulation, run the simulation, 1 second, 50 steps, that's okay. And this is exactly what we are looking for. So now we can see our progress is going well. So I'm going to save my model in order to save my changes without losing them. Okay, now we created the locked joint. It will be a good idea, very good idea, to make sure that we have we create a name, distinct name for every joint. So this joint is connecting the base to the ground. So I'm going to call this joint ground to base. Again, I start with the first body that I selected and then the second body. So this is ground to base. And because the icon is actually describing this is a locked joint, I don't need to add locked joint. So now what I'm going to do, I'm going actually to lock the other bodies. So I'm going to lock Geneva wheel to Geneva wheel shaft. So I'm going to select locked joint, Again, I'm going to select the first body. You move your cursor close to the body that you are selecting. So now it says Geneva wheel. I will click, and then I'm going to select the Geneva wheel shaft. It doesn't show. I cannot pick the geometry for this shaft. So what I need to do is to get a menu or list of all the items or all the bodies in this area. What I'm going to do, I will right click. So Adam will look at the areas, all the bodies around this area, and it will give you a list of those bodies. So now I would like to lock to the Geneva wheel shaft. So I will select it from this list and click OK. Now Adam is asking for the location. I'm going to do the location at the center of mass of this shaft. So where is this center of mass? I cannot see it. Again, I will right click, and it will give you a list of the bodies that we have. So here we are going to select Geneva wheel shaft. In actual designs, in actual realistic design, this shaft will be locked to the wheel using a key. So in order to have a good realistic design, it will be very appropriate that you create a marker at the key location and select the locked joint at the key location. What will be the benefit from this? The benefit is that you are going to calculate the reaction forces acting at this key. And when you when you calculate the reaction forces at certain point, it will be very appropriate to select it in the actual physical location, so you can get more realistic results. Again, we have the joint is created here, so I'm going to change the name. So here we have Geneva wheel to Geneva wheel shaft. So this is our second locked joint. The locked joint, next locked joint will be between this locking disc and the locking disc shaft. So I'm going to zoom in this area to ease my work. I will go to select fixed joint again. Between this locked joint, I cannot get the geometry, so I will right click. It says locking disc. Select the locking disc, and then I will get the shaft, the locking disc shaft. So I will right click and select locking disc shaft, LED shaft. Click OK. And again, I would like to select the center of mass of this locking disc as the location. So I'm going to right click. So here's the locking disc center of mass. Okay. So this is our joint created here. So now I'm going to change this joint name. I'm going to call it locking disc to locking disc shaft. I will repeat. I will lock the locking disc to the holder. So I will go to fix it. I will choose the first one as locking disc. The second one is the holder, and I'm going to lock it at, say, for example, the holder center of mass. It's okay, whatever marker is appropriate for you now, because it's not physical. So I'm going to lock it at the holder center of mass. So now I have it locked here. I'm going to change the name, locking disc LED to holder. The last locked joint between this contact pin and the holder, so it will be fixed on place. So I'm going to select this joint. I will move close to the holder. I can see the name of the holder. I will click on it. I will move close to the contact pin. I don't see the name, so I'm going to right click. Once you right click, it will give you a list of the bodies, so I'm going to select contact pin and click OK. Now it is asking for the location. I'm going to make the location at the center of mass of the contact pin. You move close to this area, right click, you will see the contact pin center of mass. I will click OK. Again, give it a name. This will be, the first body is holder, the second body was contact pin. So now I think I have all the joints in place. If I run the simulation now, what we expect is that this base is not going to fall down. And let's see what's going to happen to those systems. If I run the simulation, they are still falling down. And the reason is that we did not create the revolute joint between the shaft and the base. So this will be our next step or next task, is to create the revolute joint between the base and the shaft. So now, as you can see, our model right now, we will have the axis of rotation of the shaft should be perpendicular to the base. But the base is in the XY plane, and our grid is actually in the XY plane. So we need to change our working grid. Instead of being in the XY plane, I need to have it in the XZ plane, such that the rotational axis will be in the Y direction. How do we do this? We can change the settings from the working grid. So I will go to settings, working grid, right here, and then I'm going to select the orientation. So I would like to have my working grid in the XZ plane, in this plane. So I'm going to select global XZ. Once you choose global XZ, you can see the axis of your grid became in the XZ plane like this. And now we have our Y-axis is perpendicular to the plane. So if I created my joint now, the axis of the joint will be perpendicular to our working grid. Now I would like to start by creating the joint between this shaft and the base. So I will go to connection, select the revolute joint. Two bodies, one location, normal to the grid. Okay, so I'm going to select the first body is the base and click on it. The second body is this Geneva wheel shaft. So I will right click. You see Geneva wheel shaft is right here. Click on it. And I would like to have this joint at the center of mass of our shaft. So I'm going to move close to the marker where it should be located. It should be located here, but I don't see it. So I will right click. You will see Geneva wheel shaft, center of mass. So now I'm going to click OK. As you can see, the joint have been created perfectly. It's perpendicular to the base and it is located at the center of mass of the shaft. So now we need to change the name of this joint. So I'm going to call this joint base to Geneva wheel shaft. And we would like to repeat this for the locking disc shaft. I'm going to zoom in this area in order to see the shaft. So I'm going to zoom in this area like this. As you can see, the shaft is hidden behind this body. So it will be nice if I can hide this body until I do this task. How can I hide the body? I can go to this locking disk. This is the part right here. I will right click and select hide. So now it is hidden. It's in the model. It is here. It's not going anywhere, but it is hidden for now. Now I'm going to create my joint. So I will click on Revolute Joint. And then I'm going to click the first body is the base. I see the name of the base here. And now I'm going to click on this shaft. So now I move my cursor until I get the name of the shaft. I don't get it. So I'm going to right click and you will see list of the bodies in this area, locking disk shaft, and click OK. Now the location should be at the locking disk center of mass. Now because we hit the locking disk, I can see the center of mass is right here. So I will click on the marker. If you don't see the marker, again right click, will give you the list. Choose the marker locking disk shaft, center of mass, and click OK. Again, the joint have been created perfectly. It's perpendicular to the base and it's going through the center of the shaft. Now I created the joint. I will fit my model and I'm going to show again our locking disk. So I will go to locking disk, right click and select show. So it will appear right here. At this moment, we have almost completed all the tasks required to assemble the model. We would like to check if the model have been attached to each other. So I will go to simulation, click on the simulation and run. And exactly what we have been expecting. None of the parts have moved. So now we have all the bodies have been connected together. I'm going to rename the last joint. I'm going to call this base to locking disk shaft. And because our model seems to be working fine, I'm going to save the model. So our next step is to drive the model by adding motion to drive the input. And for this Geneva mechanism, the input is usually coming from the locking disk shaft, this shaft right here. So I'm going to add motion to this shaft. So in order to add the driver, I will go to motion and then select the rotational motion input. I would like this system to make one full rotation per second. So I'm going to change the rotational speed to 360. So now this is going to create one full rotation per second. Now I need to select which joint we are going to drive. So I will move my cursor until I see the name of the joint. Here it says base to drive locking disk shaft, which is this joint. So I'm going to select the joint, base to locking disk shaft, click on it. At this moment, we should see the system should start rotating. So I will go to simulation, run the simulation, and here it goes. So we have our model is rotating as we expected. If you would like to rotate it again, reset the system configuration and then drive, it works. What is working now is actually we have the driver is creating the motion, but we don't have contact between the contact wheel and the Geneva wheel. As you can see, the contact pin is actually going through the Geneva wheel. So this tells us that we need to add something else. And that thing is actually the contact model. We need to create the contact between the pin and the Geneva wheel. This is what will derive the Geneva wheel. How do we create the contact? We will go under forces and select from special forces, we will select contact force. This is the contact force module that we have. We are going to select the first solid as the contact pin, and then the second solid will be Geneva wheel. So I will go to I solid and right click and select pick. I will move my cursor until I see I come to this area, and I need to pick the geometry for this pin. It's not picking, so I will right click. Add-ins will give me a list of the geometries in this area. One of them is contact pin. So I will select contact pin and click OK. The second solid is the Geneva wheel. So I will go to J solid, right click, contact solid, pick, and then I will move close to the Geneva wheel solid and click. So I have solid 6 and solid 1. Those are the contact parameters. I will leave the stiffness as is, but I will just ramp up the damping. I will make it 500. And then I will click OK. If you go under forces, you see the contact force have been created. I'm going to call this contact force, I will rename it contact pin to Geneva wheel. Now if we run this simulation, we should see this pin deriving the Geneva wheel. So I will go to simulation, click on this. Now I would like to run the simulation for 3 cycles. 3 cycles will be for 3 seconds. And I'm going to make the number of steps 300, like this. I will run the simulation. And as you can see, we got the first contact. And now the Geneva wheel rotated. But see, something is not right. After the contact occurred, the first contact occurred, Geneva wheel rotated, this is perfect. But notice, in the second contact, Geneva wheel did not stop. Right here, Geneva wheel is interfering inside the locking disc. And this is actually not physical. There has to be contact between Geneva wheel and locking disc such that the Geneva wheel will not interfere inside this disc. Also, we can see that our contact pin is rotating or driving the wheel as we expected or as we would like to have. So in order to improve the simulation, what we will do is to create a new contact between the locking disc and the Geneva wheel. So I'm going to close this. I will go to forces again, create contact. And now I'm going to select the first contact is this locking disc. So I will right click, pick, and select locking disc solid 3 and click on it. The J solid, we will select pick and we'll select Geneva wheel solid 1. I will leave the contact stiffness as is, and again I'm going to increase the damping, make it 500. So the first solid is our Geneva wheel, our locking disc, solid number 3. The second solid is Geneva wheel solid, solid number 1, and we increased the damping by 500. I will click OK. You created the second contact, so I'm going to call it a name, locking disc to Geneva wheel. I will run the simulation again. I should expect it to see it better than it was before. So now we don't see interference between the Geneva wheel and the locking disc. But also you can see now we have some kind of the simulation is running slower than it was before, because now we have two contacts, and because the two bodies are in contact with each other, touching each other, this may slow down the simulation. But for now we can see our simulation looks nice. We can run the animation from this film strip. So I'm going to run the simulation. Just look at the animation. I think it's working okay for me. So I'm going to save my model. Sometimes we would like to see the contact force. How much is this contact force between the different bodies? So what I can do, I can add a measure for the contact force. Mainly we are going to be interested in the contact force between the pin and this Geneva wheel. So I'm going to right click on the force model here. As you can see, it shows up the icon here. I will right click and select measure. Again, what do we like to measure? This is the measure name. So I'm going to call this contact pin force. I'm going to change the name, contact pin force. And what we are looking for is the characteristics force. You can also look at the torque, but we have only contact force, so we're going to select the force. Now you can look, because the force is actually a vector, so you have the components in the vector or the magnitude. I'm interested in the magnitude, so I'm going to select the magnitude. Now, which force are you interested in? The force in this pin or the force on this Geneva wheel? Let's look at the force in the pin. So I'll select the first one and I will click OK. As you can see, Adams created this graphics strip for us, and as you can see here, this is actually very nice because it shows the contact is happening only when the pin is sliding inside this slot, and this pin is going to slide inside the slots once every second, because we have 1 rotation per second. So the pin is going to slide inside the slot once every second. So this is the first time to engage, the second time, and the third time. You can also look at the peak. How much is the value of the peak of the contact force? The peak is 50 Newton. And why is the peak is so small? 50 Newton is not kind of high contact, because actually the wheel, the Geneva wheel itself, does not have any load. There is no external load acting on this wheel, number one. Number two, the gravity is perpendicular to the wheel and perpendicular to our system, so there is no effect for the wheel, for the system in order to have here. So this contact force is only required to change the angular momentum of our Geneva wheel, rotate it, and then it will stop. Also, you can notice this contact is kind of noisy because we have gap between the pin and the slot, and when the pin is sliding inside the slot, you can see it is actually jagging between the two sides, and this what will create this noise in our force. So let's look at the simulation again. So as you can see, you can watch the contact force right here, and then once the pin is out of the Geneva wheel, the force comes back to 0. Also, when it engages again, you can see the contact force increased, and when it disengage, it will decrease like this. Notice here this contact between the locking disc and the Geneva wheel. These forces actually represent contact between them. Geneva wheel wants to continue with the momentum that it had before, but the disc is preventing it from motion. That's why it will create those kind of forces that you can see as small arrows. Those small arrows here represent the contact force. Our next step is to actually add an electric motor. And instead of having this motion, this kinematic motion, we are going to replace it with an electric motor. In order to define the electric motor or add the electric motor, we go under plug-ins, under controls, machinery, and you will find the electric motor is here. In machinery, actually it contains several parts. We have gears, belts, chains, bearings, cables, and the motor. So we're going to select this motor, and once you click on it, it's going to generate a new interface that will allow you or guide you in a step-by-step to select the motor that will be appropriate for your application. This interface, we call it wizard. So the interface will look like this. As you can see, for creating the motor, we have 6 steps. We have to go on those steps sequentially. Based on the selection of each step, the choices in the following step will be changed. So here we have the method that we are going to use for describing the specification of the motor. So one of the method is analytical method or curve based. If you are going to enter the motor characteristics as curve, and Adams can interpolate this curve, or you can hook it up with external source. We are going to use analytical. This is the simplest method, and then we'll go to next. Now you need to select what type of motor you have. Adams allows you to select one of 4 types. You can select AC, synchronous motor, or DC motor, regular DC motor, or brushless DC motor, or stepper motor. For this demonstration, we are going to use only simple DC motor. And then we are going for next. Now it will ask you, how are you going to place the motor? The motor will have 2 parts. We have the stator and the rotor. Typically, the stator will be connected to one body, and the rotor will be connected to the driven body. If you are talking about application like robotic arms, the stator will be connected in one of the moving parts, and the rotor is connected to the other moving part. In our case here, the motor will be connected to the ground, the stator will be connected on the ground, and the shaft will be connected, or the rotor will be connected to our shaft. So we need to define this, and we would like also to define where the motor is going to be located. So the location of the motor is defined here. The orientation of the motor is defined by the angles. and also you can specify which part will be attached to the rotor and which part will be attached to the stator. So if I'm going to start attaching the rotor to this shaft, I can right click, select the body, and then you can pick, browse or guess. So because we have few number of bodies, you will see all the bodies are right here, so you can select one of them. So I'm going to select the locking disc shaft as our body, which means the rotor is going to drive this shaft right here. For the stator attached body, I will right click for bodies, and I'm going to select the base because this is going to be attached to the base. Now, where is the location of our body? The location of our body, of our motor, I'm going to select, it should be at the base. I'm going to select the center of mass of the rotor. So I'm going to select the location, right click, and select either reference frame or pick location. I'm going to pick location, and I'm going to pick the rotating shaft, the locking disc shaft, as our center of mass. The center of mass, I'm going to pick it as the location of our motor. So now I don't see the center of mass of the locking disc shaft, so I'm going to right click here. It's going to give me the list of the marker. So this is our locking disc shaft. Center of mass does not appear here. So what I'm going to do, I'm going to hide the locking disc. Locking disc, hide. Now I can see the center of mass of the shaft right here. So I'm going to select the locking disc shaft center of mass. Now we defined our location of the motor. Also we defined the attachments. So I'm going to select next. Now those are the inertia parameters of the motor, because most of the motors are going to be fixed on the ground. You don't really need to do the stator parameters, but because the rotor is going to be affecting your system, so you need to include the information of your rotor. If the stator is attached to a moving body, then it will be a good idea to update those values. I'm going to leave them as is. Those are for the graphics, so you can define the length of the stator, the radius of the rotor, and so on. I'm going to leave the default values for now. And those are very important parameters, because those are parameters that will describe the physical structure of your electric motor. The physical structure of your electric motor will define how the motor is going to perform. So you need to look at the specification of the motor and enter the values right here. For the DC motor, it will be different from brushless, it will be different from AC, it will be different from the stepper motor. So you need to include those parameters very matching very well with your physical motor. So I'm going to leave I'm going to leave those as default values, and I'm going to go to next. Now this multiplication, this is for the motor output. Are we going to use it directly, or we are going to scale it? So we can just make it 1, scale factor 1, and click finish. We can come back and change those parameters later on. Now as you can see, there is something wrong here. The motor is actually not aligned with the shaft. It has to be rotated 90 degrees. So how do we do this? We will go for the motor right here, and are going to right click on the motor 1 and select modify. Once you select modify, it will bring again the same wizard. So we're going to look under the motor connection. As you can see, we missed the axis of rotation. So here we have the axis of rotation is defined as global Z, while in our system, as you can see, the axis of rotation is global Y. So I'm going to change the global axis of rotation, make it global Y like this. Click next, 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 finish. Okay. So now we flipped the motor geometry. As you can see, it appears down, and now we have our locking disc. I need to remove this motion because we added the motor. We don't need this motion. Sometimes instead of deleting items, it will be more appropriate that we deactivate it. So what do you mean by deactivating? It means we are going to keep it in the model, but it is not going to be active. How do we activate an element? If you right click on the motion, you see this icon here, this menu here. It says deactivate, activate. I click on this. Now I will uncheck those two boxes. It says object active. I'm going to uncheck this box. So now it is not active. If you click OK, you can see this stop sign. This means this object is not active. And now the motor should take care of driving our model. I will run the simulation and see what is going to happen. As you can see, the motor is driving because of the contact. We have the motion, and now you have the contact between the pin and the slot. It rotated the Geneva wheel, and it's still continuing to rotate. So now we have two rotations, and notice the time. We have three rotations in 1.2 seconds. 3 rotations in 1.2 seconds, which means the period time or the time for one rotation is 0.4 seconds. So the motor right now is rotating at 2.5 cycles per second. The rotational speed of this motor will depend on the characteristics of the motor, and also will depend on the input shaft, the input voltage to this motor. And as you remember, we can control those parameters from the wizard. Depending on the design of your motor, you can control those parameters, which also are going to control the torque and rotational speed of your motor. So if you go back to the motor, you can check the parameters. We can select modify. It will open the wizard for us. You can select those connections are okay now. Those are the inertia parameters of your motor, if you need to change them to match the physical model. And those are the electrical characteristics. So we have the number of conductors, we have the flux, we have the voltage. So depending on what voltage you have this source is 12 volt, number of bases, also the number of volts, and the type of the DC motor. Very important parameter is the armature resistance. So depending on what type of connection in your coil, shunt or series, those parameters will impact significantly the performance of your model. As you can see, now we have our model. You can run animation for this simulation. So we can run the simulation like this. Very nice simulation. Also, you can look at the measured. We had a measure for the contact force. So this is the contact pin force. I can view this. contact plane force. So as you can see, the force is not appearing. So let's run the simulation so we can see those forces again. In order to have faster simulation, I'm going to uncheck this box. So you can see the simulation is running here. We are now at 15%. So now, as you can see, the simulation have been completed and the contact forces as appears right here. Because now we have faster rotational speed, the contact peaks sometimes reached higher values. We can pick more realistic values for the contact model, and those peaks will drop down and becomes more smooth. That will be the end of this model.